Greetings, welcome. So this might be a pretty interesting one. If you're just starting on this penny roll series, the idea is if you have a pulse motor like this and it's spinning around, if you have it under resistance, or just the resistance of the bearing, but if you have it under resistance and you add mass to it, does the speed stay the same? Does it slow down? Does it speed up? And what's kind of curious is when you think about real life, I gave the example of like a small little two-person, Ferris wheel, and if you push it when it's empty and it goes through some branches, it would probably stop. But if you put a couple kids on there and you pushed it the same amount, it would probably just go right through the branches. Or another one I thought of is if you have like a swing and you put a brick at the bottom and you give it a push and it hits some branches, it would stop. You put like a 60-pound kid in there and you push it, and what's going to happen? He's going to say, stop it, you jerk. Why do you keep pushing me through branches all the time? So that's where we're at, but you get the idea. And it seems like in real life that it would go through the resistance more easily, but then you have a really deep conundrum, which is that going through resistance allows you to do work, and this implies that the application of a force, the same amount of force for the same amount of time, does differing amounts of work depending on whether it goes into a small mass or a large mass, which, conventionally thinking that seems absolutely loopy. But when you just think about real life, it seems like, well, I don't know. So that's why I had to look at this. Now, everything was going along beautifully until someone decided to comment. I'm not angry at the commenter, I'm angry at myself that I was so stupid that I didn't think of this, because I'm using copper pennies was the idea, and I got everything 3D printed, and he mentioned the copper is diamagnetic, that that's going to interact with the magnetic fields, and I was trying to think for a minute. It's like, yeah, it sure will. The example he gave is you can find like videos where they drop a permanent magnet through a copper pipe, and it doesn't fall at free fall speed. Once it starts to speed up, it develops a lens resistance and it falls more slowly. And I thought about it some more, and it's like, well, you always take permanent magnets and put them past coils of copper wire. So it's like, of course, you dummy, the copper is going to interact with the magnetic fields. And so I was thinking of all kinds of different ways to, you could extend the rotor up and put the flywheel up here, which would be a pretty normal thing to do, or you could extend the rotor out and put the flywheel weight out here, keep it away from the magnets. Both of them should work, but they would involve kind of rebuilding this. I have this ready to go, and I thought, screw it, I'm just going, and I'm going to see what we see. And this was, as far as I can tell, one of those rare occasions where kind of all the stars aligned, and it's sort of what I was thinking you might see. And I'm very thankful to the commenter, because otherwise, if he hadn't mentioned that, I'd be scratching my head like, what exactly is going on? But since he mentioned that, it seems to kind of all fit together here. So why don't I just do it for you, and I'll show you. So this will be like the 5th time that I've done this, and I'm looking for all kinds of ways where maybe I'm not seeing what I think I'm seeing, and just to kind of start here. So here's the rotor. This penny got wedged in, so like for the baseline, I'm going to have to put one more penny there. If the pennies weren't in, I weighed this thing and it weighs 90 grams. We're going to put 3 ceramic magnets, 1-inch diameter in each of these. I weighed those, each one weighs 10 grams. So 30 grams here, and there's 6 of them. So the magnets will weigh 180 grams. The rotor weighs 90, so that's 270 total. Then we're going to start putting pennies in. You can fit about 8 pennies in one of these. If we use copper, they weigh 3.2 grams. So let's round that down to 3. So 8 times 3, each of these slots will be 24 grams. And there are 12 of them. So 12 times 12 is 144, 288. So
we're going to add 288 grams of mass to the 270 grams of mass, somewhat doubling it. Now the momentum probably won't be entirely doubled because some of the mass will be in here. But to make a long story short, we're taking the rotor from approximately a quarter pound to a half pound. Here is the circuit, and there's just the one switch there, and we have a Hall effect sensor. The Hall goes to, I did a whole video on how to connect a Hall effect sensor to an Arduino if anyone needs to review that if they want to replicate this. But basically you've got 3 pins there, and one of them is going to the 5 volts, the VCC. The middle one goes to ground, and this one goes to your trigger one, so you put it out to the analog digital converter pin. There are 4 or 5 of those, so we're going to use pin A0. And what this does for you with these linear ones is when at baseline, the ADC will divide the analog signal up into 1024 segments. So at baseline, it's going to be spitting out a number around 512. And then if it sees a north magnet, it's going to go up towards 1000. If it sees a south-facing magnet, it'll go down towards 0. This is a monopole. We're going to have the north facing here. So all you need is an if statement to say if the value is greater than, say, 600 or 650, something like that, then turn this switch on, and you can see that the switch goes to the coil. And I'm not sure, but those look to be about 22 degrees offset. So I did it the first time, and I saw some strange stuff, and then I started saying, well, I at least got to try to make this more consistent. And so, I've glued this on. I printed a little piece for there, glued that to there. Well, I'm not gonna. You can actually adjust the height on this thing, and then I taped that in, and then I taped this in. This is our drive coil. Later we'll bring another coil in. I've kind of marked out where it was, and we'll tape that down. And I'm going to, that'll be this coil. I'm going to wind the 2 ends together and provide a dead short across it, and that will be our resistive. That'll be the load. There'll be a little bit of a load just because it's got a ferrite core, and that'll be a little bit of cogging. But the main part of the load, if you were using it to actually do something useful, you would take this and put it through a diode or a bridge rectifier out to a cap or a battery or whatever you're trying to do. I'm just going to twist the things together, and that will short it and provide a lot of resistance. So one thing is trying to make everything consistent. Now another thing that I did is I have this part here, which is where the rotor sets, and on one of them I saw something, and then it just kept getting better and better, and I'm like, wow, what's going on? And I finally realized that when I was adding the mass, this thing was gradually, with the spinning, settling more and more into just this tape that I have keeping that there. So what I've done is I've super glued this in now, so it's not going to go anywhere depending on whether we have a quarter pound rotor or a half pound rotor, because if it comes down, I think the main thing is that you're getting closer to your sensor, so your on time is becoming longer, you're drawing more power, it's spinning faster. You're also getting a little closer to the drive coil, which up until a point is probably going to make it spin faster too. So I guess I'm saying I think I've solved all, or I've addressed all of the things where I'm thinking maybe I'm not seeing what what I think I'm seeing. So here I put the magnets in. It's such a joy using these ceramics as opposed to 1-inch neodymiums, because it's not like, oh, they're stuck together, where are the pliers, and I pinch my finger or whatever. They have some strength to them, but it's not. And it was like $7, and I've got another half dozen of them left over too. Put that down there. We see how it's spinning. Well, that's not perfect, but it's pretty darn good. So I guess the very first thing we'll do is we'll just put an LED in there with the switch. And we got the rotor in with the magnets. We'll run it at 1.9 volts. And one of the things why it's nice to do that is if you accidentally put one of these in facing the wrong way, then it wouldn't light up. And this way you know they're all working. You can also kind of, as you change the code, eyeball, just get a ballpark figure, are you dealing with 50% or 20% duty cycle kind of thing. Now if I put this on the oscilloscope even at 2 volts, I'm not going to do that now. I'm seeing 100 volt spikes at 2 volts, which is even more interesting because these are 100 volt solid state alternating current relays, which I don't know if the spike is 100 volts or if it's just being pinged by the relay and then is bleeding across the relay. So when we run this, we'll run it at 4 volts, a whopping 4 volts, and there are 2 reasons for that. One is nothing's going to be glued in here. You got to be able to put the pennies in and remove them. And so if this thing starts spinning at 1,000 or 1,200 RPM, something's likely to fly off. Second is if you're running it like 8 or 10 volts, you're probably going to fry that relay because the induction from here has nowhere to go. So we'll just run it at 4 volts, and the only question I'm interested in is the issue of the mass. So it can be simple. Here's the code, and the code is simple. As we were talking about, you just have a integer called sensor value, which is that A0 pin on the analog digital converter chip. If that's greater than 630, then turn this on. If it's less than 630, then turn it off. I'm going to make one change on this 5th one, is I'm going to take this down to 625. And what that does for us is gives us a little bit longer duty cycle, which means we have a little bit more torque. And okay, let's pull this out, put the coil in, turned it up to 4 volts. I can't remember which way this thing wants to spin. That's where it wants to spin. I have a little bit of paper glued on there, so when we put the RPM meter on, we can see how fast it's going. Away it goes. So one thing with these pulse rotors is they take a while to spin up. So it takes like 3 to 5 minutes before they'll settle down into where they're going to stay. So this one unloaded seems to run right around 704 RPMs at 4 volts, drawing 20 milliamps. So we'll just jot that down on a spreadsheet, 704. Now what I'm going to do is bring this second coil in. I've kind of marked out where it was last time. And right now I'm going to leave the wires open, not connected. So the only resistance we're going to be adding is a little bit of resistance that this is ferrite and will cause a little bit of clogging. But I'm going to put that in about where it was before. Looks good. Try and tape that down. So I've just put the core in without the wires shorted and let it settle down and around 668, 670, oops, around 668, I'd say. That's what I'm going with. So 704 to 668. Now let's short that. So I just shorted it. You can even hear it slowing down. If we put the RPM meter on it, see something pretty dramatic. It's just headed for the floor. So with it shorted and giving it time to settle in, it's now spinning at right around 285. 284, 285. So jot down 285. Now, we do the experimental part. And we're going to divide the experiment into two parts. And one is going to be putting mass out here, and then a second part will be putting mass, then adding mass also in here. So the reason I'm doing that, if we put the mass out here, it's going to have the biggest effect on momentum. But these pennies are copper, and they may interact with this magnetic field, and they may interact this. So I've got this bag of copper pennies. I'm going to pour some of those out. I'm going to put 8 in each of the 6 holes around the side, around the perimeter. So I've got the pennies in now. Turn on the power, and give it a spin. And I'll be back at you in a couple minutes. So after a couple minutes, let this thing spin and settle in. And it is settling at right around 333. So let's just jot that down. 333. So now let's undo the short on the pickup or generator coil and see what happens. And you can hear it really picking up. It'll take a couple minutes to settle in. Okay, after getting this a few minutes to settle in, right around 778. Let's check one more time. Yeah. So now we jotted that number down. Okay, so the final part of the experiment awaits. That is, we're going to fill the inner part with copper pennies. Now, what's kind of interesting here is that because they're closer in towards the axle, they're going to have less of an effect on momentum than the ones that are out here. However, because they're in closer towards the axle, they're not going to be sitting over the electromagnets, and so if there's anything going on from the diamagnetic copper, it'll be greatly lessened, if not entirely gone, from the mass that we add here. So let's put this in, and we're going to do the same things that we did before. Okay, I've reconnected the short on the pickup coil, put in the other pennies, turning this on, and we'll let this one spin up. It looks kind of cool from up top, doesn't it? So let this spin up, and we're at 350, 349. I'm going to call it 350, and it looks to be about settled in. About. Might get to 351. I'm saying 350. So we jot that down. I'm going to disconnect the short on the pickup coil, and hopefully nothing flies off. You know, nothing's glued down or whatnot. And you can hear it starting to spin up. So I've let this spin a few minutes, and we are at 800 and I'm going to say 817 RPMs. So we jot that down, 817. I just think that looks really cool. Alright, well that's pretty much it. I was thinking about doing a couple minutes of discussion on all this, and screw that. It is what it is. I guess the one thing I'd say is if we go back, I did this yesterday, and shorter pulse, lesser duty cycle. And so everything was slower. The one thing I saw was initially I didn't get an improvement on these outer ones. Now I was attributing that yesterday to maybe there's some diamagnetic effects between this and this when it's shorted. But we're not really seeing that on this one. If we do a little ratio, that's the ratio of improvement in the RPMs when this thing was spinning without this shorted, and this is the improvement there, and they're pretty much identical. So what I'll say is, because here that didn't happen, and the real improvement came with the addition here, although it improved fine there. So I'm going with a definite maybe that there could be some diamagnetic effects going on from the copper, but they really get outweighed, as it were, by the extra mass. And I don't know why this one was a little different, to be quite honest. Maybe somehow the rotor was unbalanced there, and somehow it got balanced there. I don't know, but the diamagnetism is not a showstopper. Furthermore, these are all copper pennies. Now the new pennies are like 95% zinc. All of the coins have copper in them, the modern coins. I found that out. The ones with the least copper are probably the new pennies, which are about 95% zinc. So they weigh 2.5 grams instead of 3.2 grams, but add another penny there and you're fine. So that if there is diamagnetism, I'm guessing that would mean that it would get rid of 95% of it if it's a mass effect thing. But if it's like a wire gauge thing, it still could potentially be a problem. But it's not much of a problem even with all copper. So go with the modern zinc pennies, and I think that's a reasonable ballast. And I'll just kind of be silly here for a moment, half silly, not entirely. I like using these pennies. You got these little pennies of a set diameter, a set mass, and a set height. And so they fit here. So I've been looking at lead, and if I was to get lead, they don't make like 1/2-inch diameter lead discs. They make like 1 or 2 or 4 or 6-inch. And if 1 inch, it's going to be, it's not going to fit there. If you put it in there, it's not going to have as much effect on momentum. And you're going to end up spending like $50 on the lead to probably get the same mass. You could buy lead lead pellets, but then, you got to like weigh them out on a jeweler scale or something, and then try and fit them all in there because they're all like 2mm balls. And that would be a real pain. This works. And the other thing is, I'm very cheap if anything, but it is kind of cool that, they stopped making pennies. So I'm going to go to the bank next week and, ask them for, will you give me 20 penny rolls for $10? And that's going to be a heck of a lot of mass. And also it's free. It's like, if this doesn't work out, then you just put the pennies back into a roll and you take them back to the bank. So the actual stuff is actually free. Not to mention, even beyond that the pennies cost more to make. You couldn't buy the equivalent mass of zinc for the mass you can get just from the bank in penny rolls, because the pennies cost like 2 cents to make, and you're getting them for a penny. So they're like cheaper than buying anything, but also you can just take them right back to the bank if you finish with it, or you have an extra roll left. So it's kind of a nice free kind of thing. So going forward, I think the we took this from, what did we say? I think a half pound to a 1 pound rotor. So it'd be fun to take this from a half pound to a 2 pound rotor. Now, as we do that, eventually I'm going to have to make things a bit less jury-rigged and kind of like 3D print and have this in here. And then you could think about, the easiest thing to do would just be to make this twice as high, and you're good to go. You could also like extend it. Actually, I may do that. You could spin this with these here, have a layer of pennies out here, then have another layer of magnets out here. And you could have those magnets going north, south, north, south. And so when you put this in, the thing that would do for you is, now you don't have to worry about any goofy stuff going on with one wire rectification. You'd put it into a bridge rectifier and it's just a regular old alternating current. So that's probably the best way to set it up. And as you spin it in here and you're putting the mass out there, that's even more of an effect on momentum. You could also just have this here and then like run it up a couple inches and then have like a flywheel, I think again using pennies, up here however big you wanted, and that would allow you to put a second coil in here as like a pickup coil or another generator coil or something like that. When you start making this thing real long, and you're going to have to put in another bearing up here, it adds a little bit more resistance. It's just a little bit more of a pain because there's more parts, there's a little more resistance. So I think I'll probably just do the two that I mentioned, one like this a bit higher and one this a bit wider. I mean, with 3D printed stuff, I don't think I could have like a 50-pound rotor or something, but I could probably have a 5-pound rotor. So just kind of gradually work towards that and see how different approaches work. But I think before I even do any of that, because I'm kind of on a roll, get it? Penny roll. At least I have been the past few days. I want to look first at if there's any difference with battery charging now that I have ceramics here and a ferrite core, as opposed to the wrong way I think I was doing it before. And just to kind of whet your appetite, and then I'll wrap this up. The way I think I'll do that is to actually break the question into two parts. So we'll be running this thing off of, say, a 9-volt battery, and kind of anchor things in. Maybe we can get it out to like 1200 RPMs without it being scary, and have a pretty brief duty cycle and whatnot. So run it off a battery, and then just run the output through a single diode to a cap with a resistor across it. Use a potentiometer to set the resistance on the cap such that if you're at 9 volts input, you have 9 volts across your cap. Now you know that, okay, say you were going to another 9-volt battery, whatever you're getting there, that from the resistance, the amp flow. So in other words, what I'm saying, and I'll probably actually like build this out on the Arduino so that you're tracking milliamp hours out and you're tracking milliamp hours expended. So what that does for you is if there's anything goofy going on, and I'm not sure that there will be, but if there is it on the end that's going into the battery, or is it on the end that's running the machine? And I have a hunch that it's on the end running the machine. I'll maybe go into that later. But that would be kind of fun to do. And then if you did see something goofy, then you throw it out to a battery. And if not, even if you didn't see something goofy, you also throw it out to a battery and see if you see something goofy with the battery. And then you'd know it's whatever is going on that's goofy is on the part going into the battery, not the battery that's running things. All right, I've talked enough here, but I hope people enjoyed this one, and stay healthy, keep smiling. Talk to you again later. Bye.